next to noisy data. The data is there, it's not missing, but it is noisy. We have, so the readings are these blue dots. Yeah. And we kind of, we want to smooth them. So you see there are values that go away. For example, you could be measuring the speed over a street segment, and then you will have variations around the value. And maybe this is the time where you take the measure. So you have a camera or a speed sensor on the street. Cars are crossing. This is the time dimension, and this is the speed value. So you will see something similar to this. Then, yeah, you see noise. Sometimes you will see even spikes. Not because the car was very fast, it's because the sensor, it's live, yeah, it's real life. Sensors will generate some erroneous readings. So in order to deal with this, one idea is to do smoothing. Yeah, the most common is to do kernel smoothing, and there are multiple types of kernel that you can plug in the smoothing algorithm. One type of kernel is a KNN, k-nearest neighbor. Basically, if this is your data value that you want to smooth, then you look at the nearest 10, for example. In this case, k is 10, or the nearest 5, k is 5. Yeah, it's parameters that you choose. And then you average among the data element itself and its k nearest neighbors. It could be that all the k neighbors are to the right, or all the k are to the left. It could be that these k neighbors will happen in a very tight interval, or by chance they will happen in a very wide interval. Yeah? So depending on your application, you will see, do you want to use KNN, or another alternative is kernel average smoother, where you have a fixed size window. So if this is time, you say I will look at 2 minutes before and 2 minutes after. 2 minutes before, 1 minute after. Yeah, so you specify a fixed size window, and then over this window you do the average. So you average the point itself and all the neighbors in the window. Yeah? Typically, the fixed width or the kernel average smoother will give you more smooth values. This is the red, the result coming from it. Will give you more smooth values than the KNN, but it will also lose relevant information, because if you have instantaneous changes, so if your window is 5 minutes, then it will average over the 5 minutes always. But if you have 1 minute where an interesting change is happening, everyone is breaking an accident, for example, and everyone is, so you see disruption in the speed, the KNN smoother will be more able to maintain this value, but you see that the result will not be that smooth. So again, decision for you to make. Other ways is to do bidding. So sort the data and then partition them in bins, and for every bin use some summary like the mean or median in order to smooth all values that fall into this bin. So you both get smoothing well, not smoothing, but you avoid the outliers. You clean the noise, you reduce the noise, but also you get the data categorized. You transform it to categorical. Let's look at an example and then return here. So, for example, we have this data for the price for until 34. We partition into 3 bins, equal frequency. This is equi-depth. So every bin will get 5 values. So we order, and then we put every 5 values in a bin, and then we smooth every bin by its mean. So here the mean is almost 9, so we put 9, the mean is 23. We put them all to 23. You get the idea? This is what is done in the grading. So you have a mark for a course, but you also have satisfactory, good, very good, excellent. Yeah? And the idea there is that half a mark or 1 mark doesn't really make a big difference. Rather the bin. So which bin you have. So it's to smooth, but also to make equivalence between different schools. We could do regression, which was in the previous slide. So if I can find a curve, a function like the green one, that looks like the data, yeah, and then I move all points to it. So, or basically use this function as a smooth description of the data. Then if I have a weird spike, up and down or down, then I can clean it using the regression curve. Or again, use a mining algorithm that would tolerate noise. On another topic, similarity and distance. The definition can be directly known from the word similarity or distance. If we have 2 objects A and B, we want to determine how similar they are. Or the opposite of similarity is what is the distance between the 2. And this is a needed function for a lot of data mining algorithms. When we will do clustering classification in the lectures that will come, we will need some distance measure. And the general idea about the distance, it doesn't matter much the numerical value. If I say distance between 2 objects is 1.43, that doesn't mean, unless I have a comparison. For example, if other 2 objects A and C, the distance is 0.5, then I know that this distance is bigger. So it has a meaning relative to other distance values, but itself, it is not needed that the value has a physical meaning. Of course, you have distance functions that have physical meaning. For example, distance in meters, or the difference in the weight. These have physical meanings, but it's not always a property that we desire in a distance measure. For data mining, we only need to be able to compare, like these algorithms function. Yeah, so we need, for many data mining algorithms, we will need expressive distance functions that will indeed reflect the similarity and the differences between the objects. And this will depend on good selection of features and good normalization. We spoke about features. If I if I want to do image similarity, yeah, then the similarity will depend a lot on what kind of features we extract from the image. If we do model-based rather than the neural network one. Neural network is black box will deal with the thing, but if we do model-based, we will need to classify, cluster, do some similarity measures, and then it will depend on what kind of features we use to represent. But also will depend on the normalization, a topic that we will touch upon later in this lecture. The most common known traditional distance measure is LP norm. You of course know Euclidean distance. That's for points in space, in two-dimensional space, or even three-dimensional, n-dimensional space. In the two-dimensional space, Euclidean distance is p equal 2. So it's basically, it sums all the differences squared and then take the square root. So if we have points that are two-dimensional, it's x minus x1 minus x2 squared, y1 minus 1, 2 squared, square root. If we have 3 dimensions, then we have also plus z1 minus z2 squared and the square root for the result. When p is 1, that's called the Manhattan distance. And we have a special case for p is infinite. So let's try now, please do it. Compute the LP norm between these two vectors. Taking p as equal 1, and then another exercise p equal 2, and another exercise p infinite. Please try to do it.
What does P actually mean in a mathematical sense? It's just a random value? I mean,
no, not random. It's a subscript for the distance. You say I do L2 norm.
yeah.
So you see the name, it's called LP norm. So every L norm, so we have names for the Euclidean and Manhattan and the infinite,
Okay.
LP infinite. And they have convention which kind of applications we use, whatever this, which of them.
Okay.
When you do p equal 1, you are computing Manhattan. So compute it first and then use. So that's three exercises. So what is the L1 norm?
4.
It's 4. And what is the L2 norm?
4.
It's root 8,
8.
right? And what is the L infinite norm? Difficult to compute. Well, it doesn't come from the formula. So we can show that it's...
Can you show me the calculation? I was not listening to it.
I mean, the first one is 4.
Yeah.
And apparently the second one is root 8. But I got 2.
May I have your attention, please? So L infinite, because it's also a common type, it actually reduces to the maximum xi minus yi. Maximum over n over d. If we have 1 to d, yeah, it's maximum over d. Basically, it comes from the limits. So basically, we want to find limit this fraction with this expression when p tends to infinity. Sigma 1 to b. Let's call the term inside ai. So we can show that we have max ai power p and then some 1 to p would this be greater or smaller than this? It has to be greater than or equal, right? Because instead of summing AI, we are summing the maximum among AI again and again. Yeah? So this has to be greater. Well, forget the limit now, we will do the limit later. But we also know that this is smaller because it's 1 times the maximum, while here we have the maximum plus other stuff. Right? So if we do the limits everywhere, this one will be basically 1 over p max ai power p all power 1 over p, and if we take the limit where p tends to infinity, then here we have no, this is 1 over d. 1 over d, then we will have something like this. This one will tend to 1, and this one will be max AI. So we end up here with max AI, and this one without limit is immediately max AI. So this is a sandwich theorem of limits. So it will reduce to the maximum component in this interior vector, which in this case is 2. So here we have the same difference, here we have also the same difference. So it's 2. And it is general feature in the LP norm that the higher components of the vector have more effect in the function. Even when we do Euclidean, I'll show an example. So imagine I have 3 points. One point, every point is a location and a time. So one point is location, here you will be at this time at 10 a.m. Another point is symplectic cell, you know it, at 11. And another point in regime at 10:30. Which 2 points are closer? Why? Regime? Do I write it wrong?
It's good.
It's in China? So basically we have 1 hour difference and a small spatial distance, and here we have very big spatial distance but only half an hour difference. So which one is P1 closer to P2 than P1 to P3? If we do, we cannot really tell. If we directly do Euclidean distance, then we will square this one, we will square this one, sum, and take a square root, and the result will be 8,000 point, a very negligible fraction. So basically, this component is dominant. Similarly, here we have 1 kilometer and 60 minutes, so this one will be dominant, the result will. Yeah, so it's a feature in LP norm that the bigger component dominates the result. And this is why we need to do scaling and normalization. I need to look at the whole data set, all the points that I have there, and see, is it normal to have points that are very far in space in this data set? Yeah? Then the space is not that important than the time. So I need to normalize and scale the time independently and this spatial distance independently, and after that compute the cleaning.
60 minutes.
Who gets it?
Yes, sir.
Problem with this concept? Which
Yeah.
is
Time.
right. That should be P1, P3. Sorry, that should be P3 and this
Yes.
P2. Right. Let me correct it at the spot. Good. And then there is a generalized form from the LP form called the generalized Minkowski, where we basically do the same, but we also add weights. Some components in the vector are more important for our applications than other components, then we can be weighting them. Yeah, so we already covered this. So when your data is multidimensional, you have different features, and then you want to combine all of them in one number. Typically, you will use Euclidean or another LP norm variant. But before doing that, you need to scale and normalize your data in order to balance the different dimensions so that they have similar effects on the overall result. So normalization, you could normalize, assuming a normal distribution, then you normalize with by subtracting from the mean and dividing on the variance. And like this, you expect that most of your data will fit into the range -3 and 3. But of course, there is no guarantee. Some data will be out of this range. If you want to strongly restrict the data to be inside a range, for example 0 to 1, then you need to normalize by dividing over the maximum minus the minimum value in the data set. So doing this for every dimension in your data independently, you improve that the dimensions will contribute equally in the overall distance. Yeah, I show here one kind of distance that more sophisticated one for sequences, the so-called edit distance. So how Mahmoud, my name is similar to Muhammad. I hit this again and again. People will mix the two names, and now I'm going to prove that they are not similar. So how to measure the distance between two streams? Yeah, one way is to do the edit distance. And the idea of the edit distance is how many edit operations we need to do in the source string in order to reach the destination string. Yeah? So if I start with Mahmoud, how many edits I need to do in order to get Muhammad? For example, well, M matches M, nice. A does not match O, so I could do a replace. So that's one edit. H matches H, we are fine. Here A does not match, so I could do an insertion. I could insert a letter in. Yeah? So that's a second edit. M matches M, O does not match, so I could do a replace. U does not match E, I could replace, and then D will match D, so I get a match. And like this, how many edit operations? 4. So the distance here is 4. Yeah, and 4 is a big distance. They are not similar. So 4 could be, for example, the distance between John and Sina. Right? Two very different names. So that's a proof that it shouldn't be mixed. Unless you want to use Levenshtein. And Levenshtein distance, it's a variant, it's a smaller variant of the edit distance. It will penalize the replacement with 2. So it says that the replacement is basically a deletion and an insertion. So it should be penalized in 2, and like this, the distance gets here bigger, but also here the distance is going to be 8, which kind of makes sense. I admit there is some similarity, while here is very different, right? So that's a general concept of the edit distance, but it's expensive to compute. And imagine doing it for a very long sequence. For example, you do it for a gene sequence to check the similarity, how many mutations or edits in the gene sequence you need to do in order to match. That's one way to measure similarity. So we will look a bit on the algorithm to understand the complexity behind it. And yeah, we'll come to other common distance measures that basically suffer from the same problem. You may have already observed that there could be many solutions. We could, please.
Will it be the distance 7 or 6? Because 3 replacement 6 plus 1 is.
You are right again. Yeah. Thank you. So you may have noticed that we can reach other distance values. For example, instead of a replace, I could do an insertion and then an insertion there and reach another sequence of edits. Yeah, but the value will probably be higher than 4. Maybe in Levenstein it will be less. But let's now focus on edit distance. Any edit is penalized by 1. So the question is how to find the minimum edit distance. The original algorithm looks like this one. Basically, it has a stop condition and a recursive part. The stop condition is when one of the two strings ends. So I am matching a string to nothing. In this case, I basically need, if I ends, I need j. If j ends, if j is 0, I need I ends. Yeah? So the maximum, the size of the remaining string, let's say. This will be as many insertions I will need, or deletions if the source string is the one who equals. The other way around. And then the recursive call, I penalize a 1 because I remove a letter from the first string, the source string. So that's a deletion operation. So I delete 1 letter from the source string, or I insert 1 letter in the source string, and again penalized by 1, or I replace, or match. So if the 2 characters now that I'm examining now match, then k is 0. K is 0 if the 2 characters match. If they don't match, then I replace and penalize with 1. So I take the distance before this step and then add a 1 or a 0. You get the point? And of course, all these are recursive. Yeah? So in order to match, now I have another better visual illustration. So basically, we want to reach this goal to match the complete string to the complete string. Yeah? But in order to match this one, I want to find the minimum of these 3 options. Either I delete, I'm mixing delete and insert. Either I delete 1 letter from the source, or I insert 1 letter in the source, or I replace or match. Yeah? But this is for the last character, but then I have the very same choice in each of these. The distance here will be either I go this direction, or this direction. So 1 is insertion, 1 is deletion, 1 is replacement. And then I continue as such until, so this is all backtracking. This is all recursive calls until we start matching the very first characters, and we backtrack back. We backtrack to the destination. You get this algorithm? Please.
Doesn't the fact that that's strictly recursive make it super inefficient.
I agree. What is the complexity in your opinion?
3 to the power of something exponential, right?
Not that harsh.
Okay.
So analyze more, please. Think more.
3 something.
Let's start with the time complexity. Space complexity. How much space we need here?
The space of two strings,
Yeah.
like
No.
numbers or the books.
We need this matrix, right?
Yeah.
And this matrix is
M into N.
Well, M
m
by
times n, or I times j, whatever we call. Here we have I and j, or m and n.
sorry, this is the same as DNA alignment algorithm. Yeah.
Yeah. Did you do a DNA alignment?
Yeah.
Well, edit distance is a quite common way to do alignment.
Yeah.
Okay. So we need a space complexity of m times n. We need time complexity. Well, we need to compute every cell in this matrix. So it's also m times n. Yeah? And we need to do backtracking. What is the size of the stack? The backtracking stack that we need to use.
If we use looping, then it's we go M into N, like both time and space. Otherwise, it's
If we use the loop.
yeah.
Which-
If you don't use recursive call,
No, let's start with the recursive version.
for that space complexity is higher, right? Not M into N. For recursive call, because we are making different strings.
So you basically here we, if we keep looking up, because here we start with the up direction, then we will have to go like this. All these are recursive calls, and then when we reach here, we cannot go any more up. We will have to go left. Then the second recursive call will start. Then we will go all the way there. And then we will start backtracking. We will start freeing from the stack and pushing, freeing, pushing, freeing, pushing. Yeah? So it means that we need m plus n. So the stack will be in this order. Yeah, so because here I and j, I call them I and j, but call them m and n, whatever you have before to use. Good. Of course, we can do dynamic programming and break the recursion, and that's a good idea. So we initialize as such in order to change this algorithm into dynamic programming. We see that the computation will start from the top left. Even in the backtracking version, it had to do recursive calls until hitting up and then backtrack, right? So in dynamic programming, we will start by initializing these. And why is they initialized as such? Well, for beautifying the algorithm, we have this dummy character, 0 and 0. So, and there the matching is 0, there is no penalty. And then if I match an empty string to an M, this is an insertion, so penalty is 1. If I match two empty strings, M and two characters, M and A, to an empty string, penalty is 2, and so on, right? Similarly, we initialize this one, and then we either go row by row or column by column. So if I go row by row like this example, so here I have all the values that I need. I have the penalty of insertion, the penalty of deletion, and the penalty of replacement. And then I see, okay, these two characters match, right? So it's an M and M. So there is no extra penalty. I take the minimum among these three and add a 0 because they match. Then I go to this value. I have the three values around. Then I take the minimum of this one plus my own. So here M and E don't match, so we get another penalty of 1. So I put 2, but I have here a better value to start from. So I could add a penalty of 1 over this value. So we basically add 1 in each of them and take the minimum. So it will be 1. Yeah, and continue as such. So when we reach here, we are, so we go row by row. And when we reach here, we are matching a D with a D. So we could be taking the minimum among these, which is 4, and then adding a 0. So the overall, the minimum distance is 4, as we did in the first slide. Yeah? And then you can go back and find the sequence of edits that would leave, would result in this. So the sequence of edit. So now we know the distance, but we don't know the sequence of edits. But from the matrix, we can find the sequence of edits. So go with the shortest path. So if you go across the diagonal, you have a path. Or you could go like this. And you also have a path. Yeah? So you can find many paths, and when you move right, it's an insertion or a deletion. When you move down, it's the other one. And when you move diagonal, it's a replacement or a matching. Good. Now, what is the complexity of this dynamic programming variant? M times M. This is the space complexity and also the time complexity. Right? We still use the matrix and we still do M and N, M times N computation. But we do no backtracking. Yeah? So 0. Can we do better? Ideas? Can we do better? Well, there is a naive solution to go with a better space. Do we need to save the whole matrix? We did it row by row, right? And when I'm doing a row, I only need the row above.
Ah, yes, yes.
Right? Do I really need to store the whole matrix?
No. Only
So
the
we
last-
can reduce the storage, the space complexity to,
one. I mean,
well, order I or J.
Yeah.
If I do row by row, it's I, order N. If I go column by column, it's M. More or less linear order. So basically the idea is such, when I'm computing this one, I need to store this one and the one above. Yeah, and I continue scanning down. And of course we be smart to choose either row by row or column by column to the smaller. Then the time complexity is still M and N, M times N. but the space complexity is the minimum among the two. And it's linear. So at least we save some,
Space.
which is very critical. Imagine you are doing DNA sequence alignment, and what is a typical length for a DNA sequence?
I mean, very big. Thousands and
In
thousands.
terms of thousands or tens of thousands. Yeah. So if you need to allocate in the memory tens of thousands times tens of thousands, that's already a big number, right? And then you run out of memory, and only the allocation will take huge time. Good. Edit distance is a loved kind of distance. You will find it in many applications. There are many variants of it. There are variants that will add temporal, will do time warp edit distance to include if you have a time dimension in your data. I forgot other variants. I will, if I remember, I tell you. And there is a similar kind of distance called Fréchet distance for spatial and spatiotemporal sequences. Again, suffers from the same matrix complexity and can be optimized using linear programming as such. There is a graph edit distance. So here, the edit operations are insertions and deletions of nodes and edges in the graph. And you are trying to match a source graph to destination graph. This is a needed function in graph databases. If your data is histograms, then you have a kind of distance called F mover. You know a histogram is as such. So imagine we have the color histogram of an image, and we want to measure similarity between two histograms. Yeah? So Earth mover distance will consider that one histogram is hills of sand, and the other one, the bins are holes in the ground. And then the idea of the Earth mover distance is to find the minimum effort required to fill the holes with the hills. Then you have so many combinations to move a bit from here and a bit from there, or to move the whole bin. Yeah? So you need to fill one with the other. It's also an interesting kind of distance. Or looking at the longest common subsequence, especially when we do time series matching, we want to see repeating patterns. Cosine similarity, if we have multi-dimensions in the data and we want to combine them a better way than Euclidean and ignore. Yeah. Or learning the similarity. So we could learn how to find similarity, but if we have some labeled data that will tell us which pairs are similar, which pairs are not similar, we feed this in a data mining model or a neural net to build a model around similarity. It's a very interesting topic, and it's open, so I am now advising a PhD thesis on the similarity of spatiotemporal objects, and it's interesting and so many open questions. Good. So readings and credits, and we are done with this lecture. Thank you.
Thank you.